Have you ever wondered how we peek inside the brain without cracking open the skull? Have you ever seen one of those glowing brain scans on the news and thought, oh, that's what thinking looks like? Or maybe you've heard people throw around acronyms like EEG, MRI, and TMS and wondered if you've accidentally fallen into a neuroscience-themed bowl of alphabet soup. Hi, I'm Megan Puglia, and in this episode of Unhidden Curriculum, we're opening up the toolbox neuroscientists use to study the brain. Because it turns out there's more than one way to peek under the hood, and those colorful images you see, they might not mean what you think they do. Today, we're going to break down the major tools researchers use to measure and manipulate the brain. We'll talk about how they work, what they actually tell us, what they can't tell us, and how to pick the right one for your research question. So let's get started. Before we jump into acronyms, let's start with a big picture distinction. When it comes to studying the tools of the brain, most tools fall into one of two categories. Some tools tell us about the structure of the brain, what it looks like. Others tell us about function, what the brain is doing in real time. Both are essential for understanding things like development, disorder, and individual differences. But like most things in science, there's always a trade-off. Some methods are great at telling us when something happens in the brain with millisecond precision, but not so great at telling us where that happened. Others can pinpoint the where with incredible detail, but are much slower on the when. And that's not all. You also have to think about cost, how invasive the method is, and whether the task actually reflects real life. So now that we've gotten the lay of the land, let's break down the tools themselves. First up is EEG, or electroencephalography. EEG is one of the oldest and most widely used tools in cognitive neuroscience. It measures electrical activity in the brain using small electrodes placed on the scalp. What it's actually picking up? The combined electrical signals from large groups of neurons firing together, specifically postsynaptic potentials. These are tiny voltage changes that reflect coordinated activity across millions of neurons. Why we love it? EEG is fast, millisecond fast. We say it has excellent temporal resolution. It's relatively affordable, non-invasive, meaning it doesn't require surgery or go inside the body, and it's ideal for studying when the brain responds to things, like sounds, images, or decisions. What it's not great at is telling where in the brain that activity is coming from. Because the electrical signals get distorted by the skull and scalp, spatial resolution is limited. It's also sensitive to motion. Blink, clench your jaw, or move too much, and your data can get noisy fast. One thing that makes EEG special is that it's a direct measure of brain activity. EEG lets us eavesdrop on real-time neural chatter. Here's a metaphor I like. EEG is like listening to a roaring crowd from outside of a concert venue. You know something's happening and when, but not exactly who's playing what. Now, there are even more precise electrical recording methods like local field potentials or single unit recordings, but those are invasive and typically used in animal models or during neurosurgical procedures. You can think of it this way. EEG is the bump of the bass from outside a concert venue. Local field potentials, you're inside the arena, you can pick out instruments and rhythms more clearly. With single unit recordings, you're backstage hearing every note the musicians play. EEG gives us the big picture in real time, and for many human studies, that's exactly what we need. Up next is the superstar of brain anatomy, MRI, or magnetic resonance imaging. MRI uses powerful magnets and radio waves to take detailed pictures of your brain's anatomy. We're talking beautiful images of gray matter, white matter, even tiny lesions. Then there's fMRI, or functional MRI. Instead of pictures of structure, fMRI tracks brain activity, indirectly, by measuring changes in blood flow. Here's the idea. When a brain region is more active, it consumes more oxygen. fMRI picks up on those shifts in oxygen levels by measuring changes in the bold signal. That's blood oxygen level dependent. Think of it as a heat map of brain activity overlaid on those beautiful anatomical scans. Pros, it's non-invasive, widely used across neuroscience and psychology, and provides great spatial resolution, meaning you can see exactly where things happen down to the millimeter. Cons, it's slow. It lags 2 to 6 seconds behind the actual neural activity. It's expensive, and you have to lie perfectly still in a giant noisy tube. Not ideal for kids, claustrophobic folks, or certain patient populations. Next up is fNIRS, or functional near-infrared spectroscopy. fNIRS is like the portable cousin of fMRI. Instead of magnets, it uses light, specifically near-infrared light, to measure changes in blood oxygenation in the cortex. A cap or headband embedded with sensors shines light into the scalp and detects how much is absorbed, giving us insights into which brain regions are working harder and using more oxygen. Why it's useful? Well, it's cheaper than fMRI, more tolerant of movement, and way more flexible. You're not stuck in a scanner. fNIRS can be used in classrooms, clinics, homes, or even grocery stores, making it great for studying the brain at work in real-world settings, especially in populations like infants or young children. Its limitations are that it only captures activity in the outermost layers of the brain, and its spatial precision isn't as sharp as fMRI. But in the right context, especially when flexibility and comfort matter, fNIRS is gold. Next is MEG, or magnetoencephalography. MEG is like EEG's fancier cousin. Instead of picking up electrical activity, it detects magnetic fields generated by that same neural activity. Because magnetic fields aren't distorted by the skull the way electricity is, MEG gives you better spatial resolution than EEG, and still keeps that fast timing. The pros, it's got high temporal and good spatial resolution, and it's great for localizing sources of activity. The cons are that it's crazy expensive, requires a magnetically shielded room, and is not widely available. This is a much rarer technology than EEG or MRI. Next up is PET, or positron emission tomography. PET is in a category all of its own. It doesn't directly measure brain activity or provide detailed anatomy, but instead captures metabolism, how your brain uses energy to keep things running. It does this by using radioactive tracers injected into the body to track things like glucose use or dopamine receptor binding. You'd use it to study neurotransmitters, diseases, tumors, or metabolic activity in the brain. But there are some important trade-offs. It's invasive, requiring the injection of radioactive substances, and it involves exposure to radiation. It's also slower and has lower spatial resolution than MRI or fMRI. So while PET offers a unique window into the brain's chemistry, it's used sparingly and strategically, especially when other tools can't get you the answers you need. Finally, we've got TMS, transcranial magnetic stimulation. Okay, this one's different. It doesn't measure the brain, it stimulates it. TMS uses magnetic pulses to temporarily disrupt or excite activity in a specific brain area. Why it's cool? Unlike other methods where you can test correlation, how brain activity co-occurs with certain cognitive or perceptual events, with TMS we can test causality. What happens when you turn a brain region on or off? It's a powerful tool used in both research to map brain behavior relationships and clinical settings like treating depression. Limitations: it only reaches the surface of the cortex, so TMS can't target deeper brain structures. It's also not suitable for everyone. People with epilepsy, for instance, are typically excluded. And it's not always comfortable. Many people describe it as a rhythmic tapping sensation on the skull. So, how do you choose which tool to use? Start with your question. Want to know when something happens? Choose EEG or MEG. Want to know where it happens? Choose MEG or fMRI. Want something portable? fNIRS or EEG will get the job done. Want a good anatomical picture? Gotta use structural MRI. Want to stimulate and test causality? Gotta go with TMS. Want to study neurotransmitters? Use PET. Then consider your population. Can they sit still? Are they infants? Are they in a naturalistic setting? And just as important, consider your budget. These tools vary widely in cost, both in setup and in use costs. There's no perfect method, only the best one for your question, your participants, and your constraints. All right, let's bust a few myths before we wrap up. Those glowing fMRI images, they're statistical maps of blood flow, not actual thoughts. EEG can't read your mind. It's picking up patterns of electrical activity, not secret intentions. No tool gives you the full picture. That's why scientists often combine methods or triangulate across studies. It's not about flashy images, it's about asking careful, answerable questions. Brain science is a puzzle, and every tool gives us a different piece. The real skill is learning which tool gives you the clearest piece for the question you're asking. So as you explore neuroscience, remember, the methods you use shape the answers you get. Thanks for listening to Unhidden Curriculum. If this episode helped demystify some of the neuroscience alphabet soup, consider sharing it with a friend or a student just starting out. And if you want to dive deeper into how we actually analyze this data, stay tuned. Future episodes will cover hands-on tutorials on how to process and interpret brain signals like a pro. Until then, keep building your science toolbox and stay curious.